Okay, welcome back to this course on polymer chemistry. In today's lecture, we are going to discuss about amorphous and crystalline states of polymers, and with related to that we will talk about the glass transition temperature and the melting point of polymers, and then we will talk about the relationship between chemical structures of polymer chain and how it is affects the values of glass transition temperature and melting point, and I will in brief discuss about the measurement techniques of Tg and Tm. Okay, before we start today's content, let me just take 2-3 minutes to explain the last slide or last page in my previous lecture, last lecture, because I thought that I did, because of time it was completed hurriedly. I just want to spend 5 minutes there. Now, if for example, what we were doing yesterday, that I discussed that if I for example have 2 phenyl, bisphenol in this case, and now they may react with some carbonate source to form polycarbonate. Now, this example I am giving for polycarbonate, but this analysis is applicable for any polymer, any copolymer, especially for polycondensation copolymers, where you have you can find out a carbon which would signal NMR signal dependent on the two groups which is holding that bond. Now, you can have 3 types of carbonate linkage. I just give it example here, and B O C O O O B, and you can have A O C. Now, this is similar to having B O C O O. Now, these two are similar. Now, in a copolymer chain, which will be favorable? Of course, that depends upon the reactivity of the monomers, in this case A and B, and obviously the feed monomer composition. Now, for example, if we assume first that the reactivity of these 2 monomers is same, then if I take a 50-50 ratio of the feed monomer composition by mole percent by number, then obviously the chances of that AOH will react with another AOH to form a carbonate will be given by 0.5 into 0.5, because these are 50% of these bisphenols are this type. So, the chances of this carbonate linkage is forming 0.25 if I have 50-50 ratio in the feed. Similarly, the chances of this type of carbonate linkage is given by again 0.25, and individually these two are 0.25. So, together they get 0.5. So, obviously, if I having a random polymerization where it is only dictated by the feed monomer composition, not by the reactivity of the 2 monomers, then a 50-50 feed composition will produce these 3 carbonate linkage. Similarly, if I have a say 25 A is to be 25 and 75, then chances of forming ACO OA will be 0.25 by multiplied by 0.25, AOC B would be 0.25 into 0.75 again twice, because for the other way around, and for B OCOO it will be 0.75. See, for this mole ratio. So, if we found after the polymerization is made from our carbon 13 NMR that the ratio for these 3 carbonate at this for 50-50 feed ratio, monomer ratio, then we will know that it is a random copolymer. So, the reactivities are not different. Similarly, if we have this ratio of these 3 carbonates, then we will know that this is a random arrangement. And if the obtained NMR signal ratio different from any of the values for it will be supposed to for a statistical random copolymer, then we will know that blockiness is there in the polymer. So, this exactly has been shown by plotting in this. So, if we change the feed ratio, what will be the ratio of this is for AA and this is for BB, this is for AA. So, this AA carbonate or any other any other condensation polymer, and this is for BB and this is for AB linkages. So, this is the plot of monomer mole fraction versus feed mole ratio. Okay, now let us come back to today's topic of lecture about amorphous and crystalline state. Till now what we have done, we have already made the polymer. We know how to make polymer from our understanding of polymer synthesis, and then we know that how it behaves in solution, and with that knowledge we were able to find out the chemical composition of the polymer, and if it is a copolymer, what is the composition, what is the sequence of monomer present in the in the polymer, and we know what is the molecular weight of the polymer. So, we know all the basically what are the information needed for the polymer, we know by this time. So, what we will do now with the polymer? Obviously, we want to use this polymer for some applications, and I have discussed in the very beginning that polymers are utilized mainly in 2 ways. Once these polymers after synthesized are added in some formulations along with the other components, like in detergent, paint, ink, emulsions, where polymers are added with some other compounds. So, polymer is one of the components among many. Secondly, which is almost the majority of the application of polymeric material or polymers, is where the polymer is the main component, is almost close to 100% is polymers, and you have additives or fillers which basically are property enhancer or stabilizers or colorant, dye, those are the added components. So, mainly it is the polymer. So, how do you make those polymers? Like if you want to make a CD or DVD out of a polymeric material, we have synthesized the polymer and characterized. Now, we have to give, or you have to make the polymer in a different shape, which is the shape of the final applications of that polymers. So, for that we must know the behavior of a polymer in solid state. Solid state in the sense where the polymer is applied in room temperature, it is not viscous. What it is not, as we will discuss, that solid state may not be the thermodynamically correct terminology in case of polymer science. What solid by solid state I mean that it is not flowing in the in the condition where we are using. So, in polymers in that solid state can be mostly in two types, where they can be semi-crystalline. Semi-crystalline means it has these crystalline regions and which are basically ordered, and amorphous region where amorphous material where there is no order. We all know what is a crystal, and we know crystalline solid, liquid and gaseous state of matter, basically three state of matters, where in case of crystalline state, solid state, we have long range order. In case of liquid state, we have a short range order, and in gaseous state we do not have any order, and we have sharp temperature or sharp temperature condition where these two transition take place from gas to liquid state at a boiling point, and from a liquid to solid state as a freezing point. So, we know that there is three states of possible three state possible for a matter. In case of polymers, this solid state is not actually a proper in true sense solid state, because in most cases either it is fully amorphous, no long range order is present, and in second case there could be partly crystalline, partly there could be long range order exist, and partly there will be no order. So, it is a combination of amorphous and crystalline regions. So, we call this as a semi crystalline state. It is not practically possible to get purely 100% crystalline polymer because of their size, mainly because of size or large molecular weight. So, we mostly deal with semi crystalline polymer, which is basically partly crystalline, partly amorphous, and amorphous, which is 100% amorphous, 0% crystalline region. Now, what happened if we take say water and cool it down? Say for example, this case 1, if we take a water vapor and then the water, just consider water, liquid water, and then cool it down, the specific volume will go down. It will happen for most of the cases. There could be some disturbance for water, but I am talking about in general any liquid. Just consider a general liquid. We decrease the temperature, the specific volume will decrease, and at a particular temperature, freezing point, the specific will go a discontinuity, and then it will form a crystalline state, where again the specific volume will decrease with decrease in temperature, but in a much slower rate than it was in case of liquid state. Now, what happened in case of polymer? See, if I have a polymer melt, obviously there are many chains. So, if I am drawing few chains here with different inks, trying to draw polymer chains having different with different inks. Just imagine these three are the different polymer chains. In melt, they are entangled, they have thermal motions, they have kinetic energy associated with them. Now, if you cool this or reduce the temperature of this polymer melt, obviously the viscosity goes up and the polymers start flowing less. Now, if you further cool down, what happened in case of a small molecular liquid, they would have a certain temperature in freezing point or melting point, they would have arranged or form a crystal with long range order. But in case of polymers, when you are cooling, these strands, these polymer chains do not have enough space, or they do not have enough time to sort of arrange themselves and align themselves so that they make a crystal. So, to have a crystal, say for example, if I want to have a crystal, either these polymer chains should arrange in order, or they can a single polymer chain can fold like this and can make a order. So, basically if you are talking about 2-3 polymers, they can form like different crystalline states. So, what I am trying to explain, that when you cool a polymer melt, it is not possible for the entire polymer mass to crystallize, mainly because of there is not enough space, or you are not giving enough time to the polymer chains to arrange or align themselves in a crystalline manner, or maybe the polymer chemical structures do not allow them to align in a regular manner. So, if it does not crystallize at melting point and you keep on decreasing the temperature, what will happen? The viscosity will further decrease, and one point of time the mobility, the thermal energy of this polymer chains will not be sufficient to have any mobility, any long range mobility of the polymer chain. So, the polymer chain will become like a glass. So, if you cool a polymer sample, they can crystallize partly in this temperature, or if they do not crystallize at all and if further reduce, then they can undergo, viscosity can go up and they become a rubbery material, and with further drop in temperature their mobility becomes effectively very low and they become a glassy state. So, this temperature where you have a conversion or transformation of a rubbery state, transition from a rubbery state to glassy state, this is not a particular temperature, but a particular range of temperature. This is called glass transition temperature, and the temperature at which the polymer melting happens, that is the melting temperature of a polymer. So, a polymer can have amorphous material. If now we are talking about heating, what happened in case of a polymer material? For amorphous polymer, if we heat from a lower temperature region, the volume expand at constant rate, and at glass transition temperature, rate of expansion increases abruptly, and as a result of this chain mobilities, a bunch of physical behavior or the mechanical property of the this polymeric material changes. It becomes hard materials to a hard glassy materials to a soft rubbery material, and if you continue heating, at some point of time this rubbery material become like a viscous liquid. Similarly, if you take a semi crystalline polymer and heat it, after the TG, the change in the polymer behavior is less compared to a pure amorphous, because here part of the polymer material is amorphous, part is crystalline. So, changes at Tg are less drastic, since the changes are restricted to amorphous regions only, where the crystalline regions are unaffected. So, between Tg and Tm, the semi-crystalline polymer is composed of rigid crystallites, like these crystallites, which are dispersed in the rubbery amorphous matrix, and at Tm, where the crystallites melts, which leads to a viscous state. So, if I want to define a glass transition temperature, that it is the temperature at which the glassy state changes to rubbery state. What is a glassy state? It is basically, we know this is like a glass, which is a hard rigid material, which have only short range vibrational and rotational motion of the atoms, which is a hard, rigid and brittle material. And the rubbery state is basically having a long range rotational motion of polymer segments, and it is a soft and flexible. So, at Tg, what are the transitions take place in terms of molecular, if you think about polymer molecules, the intermolecular van der Waals forces, they break down, and this is the temperature onset of, that is the mark for the onset of large scale molecular motions, and we know that it undergoes glass to rubbery behavior change, and that is for amorphous polymer, obviously that should be the highest temperature of usage, because after that the polymer becomes so soft that it cannot be useful. If we talk about more about polymer crystallinity, polymers, as I said, it is never the polymer crystallinity is not never up to 100%, it is always semi crystalline, and the nature of polymer crystalline, semi crystalline material depends on how fast you are cooling, what is the condition of that crystallization generation. So, the crystallization size, the crystallites, the dimension and the shape of the crystalline regions, as well as the fraction of the entire material which are crystallized, they all depends on several factors. So, finally, whatever semi crystalline material we have, that is a non-equilibrium microstructures, and in case of semi crystalline material, there is coexistence of amorphous and crystalline region, and this is the microstructure actually determines the material property. How do you induce crystallinity in a material? We obviously can do it by cooling the molten polymer. When you evaporate a polymer solution, then the polymer chains can align themselves up, because evaporation is a slow process. Then in polymer chains in the solution have more time to align themselves, so they can form crystalline regions. Annealing is nothing but heating a polymer at a particular temperature, and basically what we give when you heat the polymers at a certain temperature, we are providing some thermal energy. With help of that, the polymer chains can slowly align themselves and form crystalline regions. And another way we can induce crystallinity in a polymer material by drawing. When you stretch a amorphous polymers, then the amorphous polymers align, just because it is we are doing stretching the polymer, the chains can come closer and align themselves in a particular direction, which basically induces crystallinity. So, these are the example how we can, these are the different ways we can induce polymer crystallinity, and as this emphasizes the fact that the final crystallinity in the polymer in extent and the nature will depends upon several processes. So, final state is a non-equilibrium state. There are different models available for polymer crystallinity. This is fringe micelle model, which is like this crystalline domains are micelle like structures. So, and these crystallite regions are formed by different polymer chains, and also one single chain can be part of different crystalline regions. So, crystalline regions are embedded with or embedded in these amorphous regions which are not crystalline. The other models, it can form just like I was explaining, it can form folded chains and align themselves to form a high crystalline material, and there are different models available like regular adjacent folds, irregular adjacent folds and non-adjacent switchbacks. Another model of polymer crystallines is spherulite, where this polymer crystallites are arranged in this manner. As a polymer chemist, we may not be very much interested in this the morphology of the crystalline polymers, but we to understand the polymer properties and the structure property relation, we must know the crystalline behavior and different types of models in polymer material. Now, how a crystalline polymers is different than amorphous polymers? As you can understand that crystalline regions, semi-crystalline polymers will have crystalline regions of high stiff regions, which basically gives you higher rigidity, but lower impact strength. Obviously, you can imagine from the structure that it will give higher density. Crystalline polymers or semi-crystalline polymers will give you higher density compared to amorphous polymers. Because of the presence of crystalline regions, it gives resistance, higher solvent or chemical resistant. Obviously, this because of the presence of crystallite, this scatter light, and invariably we get translucent to opaque material. Presence of crystallites help in reducing the permeability of different gases. The crystalline polymeric material gives high heat capabilities because of the reinforcement made by the crystalline regions, and some other properties like anisotropy and all good electrical properties you can get as a result of crystalline regions. This is not all desired. It should not have a perspective that all crystalline polymers or semi-crystalline polymers have better properties than amorphous polymers. They have some better properties, but in the cost of something else, like it always becomes opaque or translucent. If you want to have applications where you need a transparent polymeric material, then it is very difficult to do with a crystalline polymers. You always end up with choosing amorphous material. So, there is always a balance between what you need for the final applications. Now, let us talk about the thermodynamics of this glass transition temperature and the melting point in brief. Now, in thermodynamics we can have two type of transition, first order phase transition and second order phase transition. Now, from our thermodynamic knowledge we can write these expressions. Now, in first order transitions, what happened if you plot G versus any of the state parameters like temperature, pressure, volume, then it changes continuously. There is a continuous change of free energy with the state parameters like pressure, temperature, volume. Whereas, if we plot any of the first derivative of the Gibbs free energy function like V or H or S with any of these parameter, then we get a discontinuity in this plot. So, basically first order transitions gives continuity in G versus TPV plot, whereas the first derivative of G is discontinuous when we plot against these state parameters. Whereas, in second order transition, in case of second order transition, both of these are continuous functions, but the second derivative of the Gibbs free energy function G is varies with these parameters discontinuously. For example, if I consider H and then plot H versus say T, we will have a discontinuity in this variation of H with temperature. So, basically what does it mean? That the first order transitions, which in case of first order transitions like melting, where G is a linear function of it basically varies with temperature, pressure and volume continuously, and the first derivative will vary discontinuously, whereas in case of second order transition, the second derivative of the Gibbs free energy function varies discontinuity. So, if we just look at this curve one more time, the melting is a first order transition where G varies with temperature, the x axis is the temperature where G varies continuously with temperature, and the first derivative of G VHS, they varies discontinuously. Whereas, in Tg, which is a glass transition temperature, which varies discontinuity with the second derivative of the Gibbs free energy function like Cp and so C, this is to be Cp. Cp versus T would be discontinuous function, because this is the second derivative of G and these are the first derivative of G. So, does it mean that we know that Tm from these curves, we know that glass transition melting temperature is a first order transition, thermodynamic first order transition, but whether does this mean that glass transition is a second order transition thermodynamically? The answer is no, because the fact that the glass transition temperature depends upon also the rate at which we cool the polymer matrix or polymer melt. If we cool fast, then Tg will be higher. If we give more time, the polymer chains to arrange themselves and give more time, which means we cool slowly, then Tg will be lower, which means that these curves will look like same, but this temperature, glass transition temperature, will vary if we change the cooling rate or in case of reverse direction heating rate. So, this is not a hence this is not a true second order thermodynamic transition, but for a particular heating rate the phase transition between a glassy state and a rubbery state is resembles with a second order thermodynamics transition. Now, what are the factors from a polymer chemist's point of view, especially in this polymer chemistry course, we must know what are the factors that responsible or that affects the value of Tg. So, we can design the polymers of certain structure, certain chemical structure to get a desired value of Tg. Now, the main factors the Tg depends on is the free volume. Free volume is the volume occupied by not occupied by polymer. If you are talking about say polymer melt, it is the volume which is not occupied by the polymer chains. So, if you consider just a liquid, then there will be lots of, we know there are lots of intermolecular spaces which are not occupied by the molecules. So, that those are free volumes, and if you increase the with temperature, typically the free volume increases, the polymer becomes less and less, the materials become less and less dense. So, free volume of a polymer material depends on molecular weight, presence of plasticizers or plasticizing side group, cross linking. We will discuss the effect of this in little detail with examples. Another very important factor which determine the value of Tg is the mobility to rotate or the mobility of the polymer chains. If the polymer bag, for example, if it is very stiff, that the rotation between the single bond around the single bond is restricted, then the mobility of the polymers comes down. So, if that happens, then the polymer chain have much less mobility compared to a much flexible chain. So, basically the degrees of freedom for internal rotation or the mobility of the chain affect the value of Tg, and this rotation or the mobility of the polymer chain depends upon the stiffness of the backbone or the flexibility of the backbone, steric effect, side group which is basically governed by the side group present, and intermolecular forces. The more intermolecular forces, the less is the freedom to move. So, what I will do? I will take these factors one by one and give examples, few real examples to emphasize or convince you how these factors affects the Tg of a polymer material or polymer. Now, you must remember that it is very difficult to change only one of these parameters, just only one parameter, because changing one parameter, these are all interlinked sometime. So, they may changing one parameter may also change or affect the other parameters. So, it is very difficult always to attribute one change in the value of glass transition temperature Tg for a particular region, but at least we can estimate, we can find out the direction that if we do certain changes in a chemical structure of the polymers, what the expected change in the glass transition should be. So, let us first talk about the chain backbone stiffness. Okay, let us first talk about the effect of polar groups. Consider this polyisoprene and polychloroprene, cis-chloropene and cis-isoprene. This has a Tg minus 73 degree centigrade and this is minus 20 degree centigrade. Compare another set of polymer, polystyrene poly4-vinyl chlorobenzene for poly4-vinyl pyridine. The values for the Tg are given by 100 degree centigrade, 110 and 142. This is one set, this is second set. Let's compare another set, polypropylene and polyvinyl chloride. This is around 10 degree, this is around 87 degree. So, for example, here the effect of this chlorine and methyl group on the rotation, basically the steric effect caused by these two are almost similar. So, any change in these Tg values are because of the most likely because of the interaction between the intermolecular forces between the two chains. This is having more dipole, more polar. The intermolecular forces between the polyvinyl chloride chains are much higher compared to polypropylene chains. So, the Tg goes up. Similarly, if you look at the other set of examples, the more is the polarity of these bonds, the more is the intermolecular forces between the polymer chains, which causes in effect more stiffness in the chains, which makes the Tg, or it decreases the polymer mobility and which makes the Tg higher. Same here, the more polar, the more intermolecular forces and more higher Tg. So, which means if we increases the polarity of the bonds, more will be the intermolecular attraction, Tg will go up. Let us talk about effect of backbone stiffness, backbone of the polymer chain. Let us compare example of polydimethyl siloxane, PDMS. This is having Tg of minus 120, polyethylene minus 80, and say it is a much rigid backbone, polypropylene oxide PPO 200 degrees centigrade. Let us compare another set for polyamides, same class of polymers, polyamide nylon 3, Tg is 110 to 200 degrees centigrade. Similarly, we can write, you can know what is this is the number of carbon atoms which gives this number. So, 3 carbon atom, nylon 3. So, similarly, we can write nylon 6, nylon 11, which gives Tg of 52 degrees centigrade, 42 degrees centigrade, and one very rigid polyamide, polybenzamide, Tg is 500 degree centigrade. Another set of example of polyester. The Tg is minus 63 degree, whereas if I replace this with a rigid phenyl backbone, keeping everything else same, then the Tg goes up. Now, look at these three set of example, you can clearly see here we only change this CH4 backbone with a much stiffer aromatic backbone, which basically restrict the rotational freedom around this chain, which makes the polymer backbone much stiffer, and hence the Tg goes up. Similarly, example here, these two are stiff components. So, more CH2 groups we put in between, the polymer chains more flexible or less stiff. So, Tg comes down, whereas again if we instead of a non-polar alkyl chain in between, if you have a rigid aromatic groups which basically restrict the rotation around single bond, the Tg drastically go up. Similarly, silicon oxygen bond is very flexible bond. So, Tg is very low, minus 120. There is no side groups presence, which basically does not restrict at all the rotation around the single bond. That makes this polyethylene chains very flexible, and Tg is minus 80. Whereas, putting rigid group in the backbone makes the polymer very stiff, which gives the Tg very high. So, basically again if the backbone of the polymer chain increases, the stiffness of the backbone of the polymer chain increases, or the Tg goes up, or the flexibility increases, the Tg comes down. Let us now discuss the effect of steric effect, basically steric effect, or let me write steric effect of side groups. So, if you just compare a simple example, polyethylene CH2CH CH3, polypropylene, polystyrene, and 4-vinyl anthracene. Obviously, if you look at these structures, the rotation, because of the substituent present, the bulky substituent present as in each carbon atom, the rotation becomes more and more restricted with the increase in the size of this substituent. Now, you can always argue that with the increase in the size, most likely the van der Waals interaction between the chains also increases, which causes increasing intermolecular forces. Yeah, that's maybe also true. So, that may contribute in some extent of this cause of increasing Tg with more bulky group, but most likely the increase in Tg with increase in size of the side groups is mainly because of the restriction of the rotation. So, the polymer, because of the increase in the size, the polymer chain goes the polymer stiffness goes up, and hence the Tg goes up. So, which means that if we have bulky side groups, the polymer chains become more stiff, as a result the Tg goes up. Molecular weight of a polymer chain also contribute in the value of Tg, but the effect of molecular weight actually dies down after some molecular weight. So, basically with increase in molecular weight, the Tg goes up to certain point, and then basically the value of Tg becomes independent of molecular weight. It can be explained for the fact that the chains ends for a polymer chain, the ends are more mobile, more flexible, because in case the one of the sides it is not tied up from both sides, whereas any segments in between, they are tied up by both the sides. So, ends are more mobile and have more free volume, and hence they have more free volume, and if you increase the free volume, the polymer has more space to basically more space to change its conformation, and it becomes more mobile and the Tg goes down. So, for a chain, the more is the contribution from ends, the more is the free volume, hence Tg is lower. So, for shorter molecular weight, the contribution from the chain ends are significant, hence the Tg is low, and with increasing the chain length molecular weight, the contribution from the ends goes down progressively, and after a certain molecular weight, the chain ends do not contribute too much. So, the value of Tg becomes a steady value. Generally, we compare for polymer application, we take molecules use polymers having molecular weight much above than this. So, for practical purposes, the practical range of molecular weight which usually used for applications of polymers, they do not change the Tg with molecular weight. Next, talk about the effect of plasticizing side groups. Let us see particular example of so meth acrylates. Let us talk about example of meth acrylates. If R is CH3, which is methyl methacrylate, the Tg is around 105. If it is ethyl, 65, N propyl 38, N butyl -2, N octyl -42, and in lauryl -62 degree centigrade. So, look, if you further apart from the backbone, then if we keep on increasing the chain length, what happens with the further increase in the chain polymer side chain, they do not contribute too much in the restriction of the bond rotation. Whatever restriction have been imposed in the bond rotation, they have done by first few atoms. So, if you put further substitution, they actually do not contribute much in terms of restriction in bond rotation, but because of their mobility, the side chain mobility, they generate lots of free volume, and hence the entire polymer chains becomes more mobile. So, as a result, the Tg drops. So, if the side chain molecular weight goes up or size goes up, the Tg grows up. This is nothing but sort of plasticizing effect, as if these molecules are dissolved in the polymer of this. Okay. But if we compare N propyl substitution with isopropyl substitution, then the Tg goes up little bit, 38 to 50 degree centigrade. Compare N butyl with isobutyl and tertiary butyl substitution, this is 29 and tertiary butyl is 64 degree centigrade, whereas this N butyl is -2, isobutyl is 29, tertiary butyl is 64 degree centigrade. So, look here, because now this, when you have this isobutyl and tertiary butyl group, they are becoming bulky in this way, and whereas N propyl groups, they are becoming bulky or increasing size. So, the free volume, because of this long chain, is much more compared to the free volume produced by a bulky groups having a spherical type shape or coil type shape. So, they gives actually less free volume to the polymer chain, and also they may contribute little bit about the restriction in the chain rotation. So, they actually increase in the polymer increase in the restriction. So, next talk about the plasticizer. Plasticizers are nothing but small molecules which basically dissolve in the polymer matrices, and like the solvent or some added molecules, if some residual solvents is present in the polymer matrix, then what happened, because of these solvent molecules or small molecules, the free volume goes up, and hence the polymer mobility goes up, and then Tg also goes down. So, presence of plasticizer makes the polymer Tg comes down. There are few other factors which affect Tg, which does not have any generalization. I just quickly go through that. For example, if I have a compared to symmetric substitution, like 2 substituted F versus 1 substituted F, the unsymmetrical have the higher Tg. This is the 2 example. And now, the cis-tern isomers for diene polymers, they have different Tgs. Now, these are all specific examples, so no generalization can be possible. So, general explanation is little difficult to give, and the glass transition temperature also depend on the tacticity of the homopolymers. And for example, if you look the Tg of syntactic polymethyl methacrylate is different than isotactic, whereas for polystyrene is not different. So, what I will do, I will stop today, and we will start in the next lecture. We